Okay, let's take a look at CPUs. I love the fact that there's CPU information right in this book, and it's fantastic that it's here. It actually covers some more information, or I should say different information, than the technology fundamentals course does. Now, I'm not going to get super into all of these things that it's talking about. I'm going to talk about some things that are happening within CPUs that people should be aware of, and where we see CPUs within the operating system over here in Task Manager under Performance. So we'll take a look at that. So first off, in my 100-170 course, I talk about the differences between RISC and CISC, which they also start to talk about. And basically what you need to understand is that RISC has been around for a very long time. Reduced instruction set computing has been around for a long time, and so has CISC. And CISC gained has gained success from the beginning of the computer in the 70s until now, initial success, because it used a lot less registers, it used a lot less RAM, and therefore your system that you're putting together is going to be a lot cheaper because you don't have to worry about that as much. But of course, as things have become cheaper than the RISC way of doing things, meaning let's focus on what the computer needs to do most of the time and optimize our CPU for doing that thing, is really paying off. It really is paying off. And so again, if we look at computing, all of computing, while this class tends to focus on what you're doing on a desktop, if we look at all of computing, ARM or RISC processors are predominantly everything that we use. And that switch has happened with mobile. So as mobile went and pushed forward, CISC was left behind because the mobile processors themselves needed to be very power efficient and energy efficient. And so when we look at that, CISC is not really a good way to do that. So when mobile first starts getting going, Intel tries to do a little bit with it. Again, in 100, I talk about the fact that they own strong ARM and ditched it. And they try to use Atom processors and things, but they honestly have no answer, because the hardware and how they're designing it is just not designed to use a low power, where ARM or RISC has that built into its nature. And so as mobile just boom, blew through the roof, so did RISC processing or ARM processing. And I want to show you a couple of things here. All right, this is Apple's M1 processor. One of the things you should understand as you go through this information is that you are dealing with electrons, and putting all these components together in a smaller space increases some speed. And so that's why they talk about this nanometer process, which is not a direct comparison, which is terrible, because they'll say, oh, this is 5. That compares differently to this other person's 7, and it's crap when they do that. But we should understand that when we shrink that down, we are getting those components closer together. We are speeding things up because an electron is very small, and moving from one side of your screen to another side of your screen is massive. It's like going across the United States, right? Even though they're really fast. And so part of what you're seeing here on the screen, Apple's M1 processor, is basically putting that stuff together, closer together. So you'll notice down here, right, here's the 8-core CPU, the central processing unit, and then there's the 8-core, GPU and CPU. So they're putting that together, where in a standard gaming system, right, you've got to have this massive processor that's dealing with all your graphics, your gaming graphics, and it's separate from your CPU, and they might as well be a million miles away. Because of how far they are away in the system. So putting them closer together increases that speed. Now, lots of people are upset about this, mainly just because Apple did it. And the honest truth is I don't know why anybody waited for Apple to do it. I just can't figure that out. It's kind of like people, I don't know. It's just weird. Apple and Intel had a really tight, not joking, a business model together. They actually developed this together. Thunderbolt is mostly a Intel thing, but they developed it just somewhat in conjunction with Apple. They had a very, very tight relationship. And so what motivates a company to stop using an i7 or an i5 that Intel is making and has been doing for them for such a long time? Why would you do that? And some, people out there that are, say they're in the business will say, oh, it's just because they're arrogant. Apple's arrogant. That's why they did it. It's like, no, they weren't getting what they needed. And that's really what it comes down to. Any organization, if they're not getting what they need, risks losing their competitive edge. So in other words, if I'm relying on Samsung's chips, or I'm relying on NVIDIA's chips to get some things done, and they're promising me that this is going to happen, and then the timeline comes up and it doesn't happen, and then they say, well, it's going to happen next year, right? I'm risking falling behind. So this is an ARM design. You can go and look that up, but Tegra's ARM design, Samsung's ARM designs, TMC ARM designs, Apple ARM designs, they're all basically using the same core design. And then they're modifying this to what they need the system to do. And so why am I showing you this? This is definitely a change in CPUs, and it is changing fundamentally everything. I use it in my 100-170 class to kind of show that not much has really changed in the Intel area. And by that, I mean Intel AMD area. Not much has changed there. Basically, over the past years, increasing performance by a few percent, 5% at the most, which is not noticeable by anybody. And so you really don't need to get a computer, and even in 3 years, right? That's what we used to say. You got to have 3 years, you got to, and then they extended that to 5, right? 5, 10, 15, 20, 25%. So I'll buy a computer every 5 years and I'll see the 25% bonus. 3 years, 5, 10, 15, I won't see the performance difference. And that's pretty shoddy. Now, you wouldn't know that because most of you are not old enough to know that, but I remember the days where you're doubling speeds. The next year's model is doubling the speed, and that's significant. And that died off and it stopped happening. And so that's what somebody like Apple that produces everything, the operating system, they produce the hardware, they can turn quicker than somebody that's waiting on another company to do it. And so what happened is they just got to the point where, hey, Intel, what's happening? Hey, Intel, what's happening? And you have to understand that these companies are sharing data between each other that's very secretive, that they get sued if they released. And so Intel's showing them this is where we're going to be in 10 years. And then obviously on the inside, Apple must have been looking and going, that we want to be well beyond that in 10 years. And so then having to make that split and do something different. And this has made huge, big news because you're talking about a 16 billion transistor processor that's got 8 cores for a GPU, 8 cores for a CPU, and 16 cores, so equaling those for a neural engine. And I, always point out to students, that's AI, right? So we know a machine learning and AI is the next big thing, and it's going to change things dramatically. And here they're saying we built it in. So we built in a place for this to be done without having to tax a CPU or a GPU to do so. Then you've got the M1 Max up to a 10-core CPU and 32 GPU, right? 57 billion transistors. And what it's doing, right? It's still a 5-nanometer process. So that's the M1 Max, and they're on to the M2, which is even better. And as I said in other classes, this one was faster than any i5 that was out at the time, and faster than almost every i7 that was out at the time. And so that really trounces if you can come out and say, there you go. And Intel is just like left going, holy crap. Intel shouldn't have been left saying, holy crap. They're the CPU people. They could look at because this is not brand new, right? This is coming off of their mobile processor designs for their A14s or 13s or whatever. And so they should have seen this coming, right? They should have seen it coming. The business, we know the business model is all, not all, but mostly pushing to mobile. You're just a flood of mobile, and you're Intel and you're not in the mobile game. You don't make processors for mobile. And it just seems like Intel just kind of stuck their head in the sand and said, well, forget it. We won't do it. There's actually a consortium called RISC-V or RISC-V, and RISC, right? ARM is based on RISC, that Intel could be a part of, right? They could be saying, well, we're making the next stuff, and by the time you get this out, we'll have something even better. But that's not what they did. As I said in other classes, they made an i9 that can beat this and stuck it in a notebook, but it can only beat it based on power usage. And people, I have students that just don't understand what's happening here. They try to boil things down to, is something more powerful? If it is, then it's the winner. Well, we have moved mobile. We have. And that's going to continue to happen and happen. And people want a notebook that's going to last 10 hours, 12 hours, 13 hours. They want a tablet that'll do the same. And they want speed. They want all of that. And so what they're showing here on this one is, okay, well, our M1 here is going to be faster than almost every laptop chip that's out there. And it'll gain that performance at basically a much lower CPU, much lower power usage. So we're more powerful chip, and we're more powerful at a lower wattage, meaning that, boy, if we added more wattage, right, we could really blow the lid off of that, right? So we can do this at a lower wattage. And that's a huge, huge thing that's happening in the industry. So as you go through this chapter and they talk about the standard stuff that we've been doing for a very long time, realize that there is a bunch of stuff happening. And no, it's not just Apple. I hate to say it, but Intel has really been left, just sitting around, because there's been a big push on the server market. Amazon AWS, and wanting more power, more processing power for the millions of computers that they use. And so there's a lot of companies that are pushing the top end of that, using the same kinds of philosophies and designs in order to achieve the goal. So this is not a secret. This is not something that's like, oh my goodness, look what Apple did. Nobody ever thought of that. No, there's a ton of companies doing it. It's just that for some reason, Intel's kind of sat around and not done it. I would suppose that's where you get really way too into the business stuff, where you got people in business that, they really don't care about that. They're maximizing their dollar. And then finally, when we really need to do something, we'll start working on it. And of course, the danger in that is will you be left behind in that process? And that's something that we don't know. So let's take a little bit, let's a short look here at some of the stuff we've got in the CPU, and I'm going to use our task manager to kind of show you what's going on. So here we are. I've got the CPU, and the CPU can go up to speed 418 currently. So the base speed is a 3.2, so that's the slowest this CPU is going to go. And many years ago, really what happened is you had one core per one CPU. And what that meant is that the faster the CPU was, it could kind of fool you in what it was doing. It was switching around and doing all sorts of things, and it was multitasking, right? It was really doing one thing and really fast, and another thing really fast, and another thing really fast. And because it was so fast, we could do multitasking. Well, Intel basically got to the point where the speed could not increase reliably with the wattage it was using and with the amount of heat it was producing. And so they said, we need to start adding 2 CPUs into a system. And I think they really like the idea of systems just starting to add 2 CPUs. But that didn't happen, right? CPUs are already expensive. If you go out and look at an Intel CPU, they're not cheap. And so you're really going to add $200 to every computer if you're going to add another separate CPU to do processing. So what Intel ended up doing was putting basically 2 CPUs together. Now, once you've done that, then now you need another term, right? You need another term, because are those 2 CPUs together? Do you market them that way? This one's got 2 CPUs in it. How do you deal with that? And so what they ended up doing is saying these are cores. And so this has got 8 cores. So 1, 2, 3, 4, 1, 2, 3, 4, 8 cores. And that basically is like having separate CPUs. So they're running really fast, and you can see that we've got multiple things being thrown across these. So now we actually have a full multitasking system. And you can see that, wow, it's actually doing some processing here across these multiple CPUs or these multiple cores that are inside, which is fantastic. Now you will note that, oh, well, wait a minute, you've got double that, so that's 16. And you'll see that listed as a logical processor. So it's got 8 cores with 16 logical processors. So what they're doing is some sleight of hand. What they're doing is basically saying, using pipelining and other things that really get into the details of CPUs. What they're doing is basically saying, we will pretend like there's 2 processors or 2 cores per core. That way, as the operating system, you can start making a call and processing here and make a call and processing here. And so that one core now gets more effectively utilized because you got these 2 channels that are pumping this information in. And so that's where you end up with, oh, you've got 16 logical processors, logical meaning they are not physical. You do not have 16 actual processors. Instead, you have 8 actual processors, and you're doubling that up. And so that's spread across. You can see how those channels are being used and what the processor's doing, because you still are dealing with the fact that the processor is super fast. It's really, really fast. And it can be just having a millisecond of downtime. Well, why not use the millisecond? Why not have another line to speak to that and do something with that process? So that's not the same thing as programming threads, just to point that out. But that's kind of how that is implemented. And so you see this CPU, and I've got it split out. I've got it split out so you can actually see the utilization over 60 seconds. And which of those is, and I can change this so that it doesn't show all of these. It actually just shows one. There's our overall utilization, right? So even in this processing of whatever it is I'm doing, I'm not using hardly any of the CPU. However, again, this is an AMD CPU. As you can see, it's a Ryzen 7 with Radeon graphics built in. And then I've also got NVIDIA graphics here. So see, there's the AMD doing some graphics processing, and here's the NVIDIA doing graphics processing. In any case, you can kind of see the similarity, right? You can kind of see that, okay, so what they did was they slammed all that stuff under one hood instead of having it divided out like I have here, where I've got memory located in one place. Got these 2 GPUs, they're located in 2 different places. One of them is actually in the CPU, right? And then the CPU has got a bunch of different stuff going on. We just tried to put that all together, right? And that does. Just this model here is going to speed things up, let alone any other technology advancements that you're doing. So that's where we find this. That utilization is right here in Task Manager. You just load that up, and usually Task Manager looks like that. You say, show me more details, and go to performance. And that's awesome. So I'm using 10 gigs of memory out of my 16, and that's because you're not aware, but I've got a virtual machine running as well, and it's using some of that too. So yeah, I'm using quite a bit. So I'm glad I've got that much. It helps me to be able to make these videos pretty easily and have everything running without a bunch of glitches. Anyway, that's some general stuff about CPU. Let's take a look at a little more in just a sec.